Let us move on to the next classification of isolated singular point, which is called pole. Now, how do we define this pole? First of all, we consider an isolated singular point Z0. We will have to check whether this isolated singular point Z0 is a pole or not. In order to check that, what do? Let us see if there exists a positive integer m such that the limit z tending to z0, z minus z0 to the power m into f of z exists, provided the limit should be finite and non-zero. So this is the condition we need to check additionally for an isolated singular point, whether the limit exists or not, provided the limit should be finite and non-zero. Now, how are we going to identify whether isolated singular point is a pole or not mathematically in a function f of z? Let us consider a function f of z, which is e power z by z square. Now, let us represent e power z first of all like this. E power z can be written as 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus so on as a Taylor series. Now, what do? Just find what is e power z by z square. So, this will give us 1 by z square plus 1 by z plus 1 by 2 plus z square by 3 factorial, and it goes on. Now, this is a Lorentz series. E power z by z square is a Lorentz series where we have positive powers of z as well as negative powers of z. One thing we would observe here is that we have finite number of negative powers of z. So that will tell us that z not equal to z is a pole. Okay, we should have finite number of negative powers of z in the Lorentz expansion. Now, the next way is to identify the isolated singular point as a pole using the limit. Now, by the definition, we have limit z tending to 0, z minus 0, the whole power m into f of z. F of z would be e power z by z square. So, this will give us, and here m is 2. Here m will be 2. So, this will be, when you apply the limit z tending to 0, it will be just 1, which is not equal to 0 and finite. So, the limit exists. Therefore, the isolated singular point z not equal to 0 can be called as a pole of order m, where m is 2. Now, this can also be visualized using a 3D graph. You can see this here. So, the function f of z is e power z by z square, and you can see that the function is unbounded in the neighborhood of z equal to 0. So, this is how it is, and it is called a pole maybe because of the way it looks. It is unbounded, it goes on like a pole, like a pillar, where you will have no other poles around it in the small neighborhood. So, this f of z is equal to 1 by z minus 4 the whole square, and f of z is equal to 1 by z minus 4 the whole cube. So, here we can see that the isolated singular point is z is equal to 4. You know how to find it. Now, here z equal to 4 is an isolated singular point, and we are going to check whether it is a pole or not. So, in order to check whether it is a pole, you will just simply find what is limit z tending to 4, z minus 4 into 1 by z minus 4, which will be just 1. Okay, so the limit exists, it is finite and non-zero. So, therefore, z is equal to 4 is a pole. Now, here for the first case, the pole is of order order 1. Here the pole is of order 1. Here the pole is of order 2. Here the pole is of order 3. Okay. Now there are variations when the pole differs. Now the thing is, as the order increases, the denominator will tend to 0 faster, which what happens will physically force the graph to turn vertical almost instantly. So I can see that the order of the pole measures the severity of a singularity. That can be visualized from the graph below. Just look into this graph. I hope it is clear and visible. Okay, in the first graph, you can see that is for 1 by z minus 4. The second is for 1 by z minus 4 the whole square, and the third is for 1 by z minus 4 the whole cube. Now, as the order increases, the spike at z equal to 4 becomes sharper, narrower, and rises to a greater height. You can just check this here. So here you can see how it is, whereas here it is going a bit narrower, and here you can see it is much more steeper here. Okay, so that's how it varies. So here z is equal to 4 is an isolated singular point, which is a pole because it satisfies the condition limit z tending to 4 z minus 4 into f of z. Points, the isolated singular points here are z is equal to plus or minus I, because we equate 1 plus z square to 0, and then we get it as z equal to plus or minus I. Now to check whether it is a pole or not, first we will do for z is equal to I. So using the limit expansion, find limit z tending to I, z minus I. So here it will be the whole cube, because we will rearrange this given function this way, z square by z plus I the whole cube into z minus I the whole cube. That's because this is being written as z plus I into z minus I. So now while finding the limits for z equal to I, here it will be limit z tending to I, z minus I the whole cube. We know what is the definition for pole of order m. So z minus I the whole cube into f of z. How is f of z being rewritten? Z square by z plus I the whole cube into z minus I the whole cube. So now you can just apply the limit z tending to I here. So this will become I square by, so here it will be 2I the whole cube. So in other words, we will have I square, so it will become 1 by 8I. You can just multiply and divide by I, so that this will become minus 8. Okay. So the answer will be minus I by 8. So this is of course finite and non-zero. Therefore, I is a pole of order 3. Now coming back to z equal to minus I. Now to find the limit for this, just find in a similar way limit z tending to minus I. Then here you will have z plus I the whole cube according to the definition into z square by z plus I the whole cube into z minus I the whole cube. So here again you can just find the limit. Of course here also it is finite and non-zero. Okay. Check this out. Find the limits. It is true. So I want you to check. Here I can see that I and minus I both are poles of order 3. Okay. Now in problems like this, the best way to identify whether the isolated singular point is a pole or not is using the limit method. We need not go for the Lorentz series method. Compared to that, this will be easier. Now this function can also be represented and visualized in a 3D graph, where you can see the poles at z equal to I and z equal to minus y, which minus I, which corresponds to the point 0, 1 and 0, minus 1 in the xy plane. You can also see that the functional values from the graph, okay, the functional values near the poles are becoming larger and larger, okay, whereas away from the poles, it is the functional values are smaller. So this will give you an better idea. You can just think about it. Let us go to the next example. Here you will check whether z is equal to 0, z equal to 5 and z equal to 2 are poles or not. You're going to check it. Okay. And here if they are poles, z equal to 0 is a pole of order 1. Here z equal to 5 is a pole of order 2. Z equal to 2 is also a pole of order 2. Okay. And another thing to be noted is that when a pole is of order 1, it is called a simple pole. A pole of order 1 is called a simple pole. Okay, this has to be noted. Fine. So let us move on to another example. These are all small examples which you can just try. Another example is this. F of z is equal to cos 2z divided by z square plus 1 the whole square into z square plus 16. Okay, so this is another example. Here the poles are just equate the denominator to 0. You will have z is equal to plus or minus I and z is equal to plus or minus 4i. Just equate z square plus 1 to 0 and z square plus 16 to 0. You can see that I and minus I are poles of order 2. Plus 4i and minus 4i are simple poles because they are poles of order 1. You can just check it from the power here. Here m is 1. Here m is 2. Equated to 0, you will get the poles. Plus I and minus I are of order 2. Plus 4i and minus 4i are simple poles. Okay. So having this in mind, we will just end the topic on poles and we will move on to the last classification of isolated singular point, which is the essential singular point. Okay, we will move on to that. Essential singular point. Now we have seen what is a removable singular point and also we have seen what is a pole. If a isolated singular point is neither a pole nor a removable singular point, okay, then it is an essential singular point. Just note it. This isolated singular point should neither be a pole nor be a removable singular point. Then it is said to be an essential singular point. Okay. Now, how are we going to check whether z equal to 0, the isolated singular point here is an essential singular point or a pole or a removable singular point? Okay. Now, we will just expand this as a Lorentz series. E power 1 by z can be expanded as, we know that e power x is 1 plus x by 1 factorial plus x squared by 2 factorial plus x cubed by 3 factorial and it goes on. Okay, so here we can have this as 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube and it goes on. Okay, so here I can see that there are infinite negative powers of z. Therefore, z equal to 0 is an essential singular point. Why? Because it is neither a pole nor a removable singular point. Because if it is a pole, it should have a finite number of negative powers of z, which is not true here. And if it is a removable singular point, it should have no negative powers of z. Both are not valid here. Therefore, z equal to 0 is neither a pole nor an removable singular point. Therefore, z equal to 0 here is an essential isolated singular point. Thank you.